Hi everyone! We're starting a free open lecture in our Discord channel. All our lectures are held daily, without breaks. If you're a viewer and want to ask questions and get answers online, then join our lectures. You can find the link to Discord in our Telegram channel. To find out the time of the lecture, join our Telegram channel and Discord. Consisting of positive integers, we can perform an operation on it that consists of three actions. First, we choose a pair of elements, the ith and jth. Then we take one of the divisors of the ith number, some number, and we divide the ith number by that chosen number, while multiplying the jth number by that same number. We need to understand if we can make all the elements of the array the same by applying this operation a certain number of times. So here's an example. Din 221. Basically, by performing two operations, we can make it equal. First, we'll choose 101 and 10. We'll divide 100 by 10 and we'll get 10. We'll multiply 1 by 10 and we'll get 10. So we already have three 10s. We just need to make the 2 and 50 into 10s. How are we going to do this? Let's take, of course, 50 and 2, and let's take x as 5. We'll divide 50 by 5 and we'll get 10, and we'll multiply 2 by 5 and we'll also get 10. So in this way, the entire array will become equal to 10. We have up to 2000 input data, but n across all sets does not exceed 10 to the power of 4 in terms of the number of elements. In the array does not exceed 10 to the power of 4. So we can basically ignore our pace. And the ith can go up to 10 to the power of 6. Here, the ith is an important thing. And if we can, we should simply answer yes for each set of input data if we can, and no if we can't. It's all very simple. It's worth noting that since this operation can be performed any number of times, the number of prime divisors, actually numbers inside this array, because everything else doesn't really interest us much. We don't need to actually implement these operations like some other problems. For example, we might be asked to do this. So if a prime divisor, well, for instance, 2, 3, 5, so on, appears in times, n and so on, 3 and some constant n, 1. Therefore, we can distribute this number, for example, across the array, well, this multiplier across the array evenly in this case. So, as you can clearly see, that's how it happened right here. Here we have the prime divisors 5 and 2 only, and the 5 appears 5 times, and the 2 appears 5 times. So, after a certain number of operations, we can distribute all the sets of 5 in such a way that each set appears in each cell exactly once, and each duplicate appeared in each cell exactly once. How are we going to do this? To do this, we need to factor the numbers and just store the results of these factorizations somewhere. Factorization is the process of breaking a number down into prime sets. Since there's a limit of 10 to the 6th for each number, and we have numbers up to 10 to the 4th, we can just use a regular docordina. Actually, we'll end up with 10 to the 3rd times 10 to the 4th, and that's already 10 to the 7th, and that's going to work. I decided to do something differently here. I took and made a sieve and a rotosven to do this even faster with even greater speed. So the sieve and the rotosven filter out all the prime numbers by systematically eliminating non-prime numbers from a list, leaving only the primes behind. I'm getting, well, some kind of set, a series of these prime numbers that are crucial for various mathematical applications and computations. And then I factor it into our map, which involves integrating these prime numbers into a larger framework or system for further analysis and use. We need to set it up. For each of these prime hours, there will be a mapping of the prime hour to the number of times it appears. Let's call it that, in the array. And then, when we simply factorize all the numbers, we have to go through our map and check the numbers. Our mapping is just that. The results are divided numerically by n. If it divides, we continue. If it doesn't, we output null and just literally end the function. Well, that's actually what's happening here. The rotosven sieve is being built, a simple algorithm for finding prime numbers. And then we reading m is equal to n for me, just because I decided to do it this way. To create a vector of these numbers, we could create it, essentially, we could create it Essentially, it's important because we can just factor it right away in this case and create a map that will store the mapping of the prime number to its count. Then we read the number n, of course, and factor it n times. That's how it goes. If there's at least one number that doesn't divide by 0, we output it, essentially. Overall, the solution works in approximately between 7 and 70 seconds. The factorization solution without the sieve take a bit longer, but it would still work.
Want to become a great programmer? Subscribe to our Telegram channel.